Okay, then we can continue our lecture on convolutional neural network. So in our last lecture, we have discussed the convolutional neural networks, the formation of that. And then we have discussed the convolution operation, both 1D and 2D convolution. And then we also discussed about the output of convolution operation based on the, that is the filter size, and based on the straight and padding options. So as we can see in convolution workflow, we can see that in this network, the first phase after taking the input is a convolution. This is convolution layer. So we have discussed already this convolution layer. The next phase here is the pooling layer. Okay, so this is pooling layer. And now I want to discuss this. That is the pooling. The pooling, actually, it is also called the subsampling or subsampling layer also, sometimes we mention. So there are several types of poolings. Popularly, we have three types, that is max pooling, min pooling, and average pooling. So from the from the output of our convolution operation, we just apply the pooling operation on it. So if you can remember that we have used two filter, filter 1 and filter 2. The when we apply the filter 1, then the output of the convolution is this feature map. And when we applied the filter 2, the output it was this feature map. So if we can go back to this image, and then this was the output. Okay, so that's our output of conclusion using filter 1. So here this one is that. Okay, this is the filter 2. After applying the filter 2, the output is this. So that means now we got our feature maps from filter 1 and from filter 2. Then we can apply the pooling on it. The pooling is kind of the subsampling. Subsampling means if we want to reduce the number of pixels, or we can say if we want to reduce the size of our input, then usually we do the subsampling. But the subsampling, it will ensure that it will keep the originality of the input. So that's why in case of the subsampling, we need to follow some procedure for that. So if we consider about any image, maybe usually what we get, that is the same colors pixel nearby. So maybe we can say if we represent those pixels, maybe out of the 100 green color pixels, if we can select or maybe 25%, then it will not actually degrade the quality, or we can say it will enough to analyze. Lose some of the pixels, then still it will be the same. Like here. So this is image of a bird. If we do subsampling, okay, if we do subsampling, maybe we will get still distorted structural. So that's why we can apply subsampling. But this is not true for all the cases. Okay, that's why the pooling operation usually we apply on those cases where if we subsample the data, then it will not lose the structure. But for some cases, actually, we should not do the subsampling. Okay, like if we consider a structure of a text, so if we do some subsampling, yeah, if we lose some of the characters of, from the word or from the sentences, then maybe we will lose the meaning of it. So on that case, we have to apply the pooling operation carefully. Okay. So so what is the pooling operation? And here, if we apply the max pooling, so for pooling, specifically we need to define the size also. That is the pooling size or pooling filter size. So here in this case, we assume that our pooling filter size is 2 by 2. Our pooling window size is 2 by 2. And straight is also 2. I'm sorry. So straight is also 2. So in this case, we can see that that is for the 2 by 2. That means we have this output from our conclusion layer. Then we have to just take the 2 by 2 subsamples here. So 2 by 2, in this case, we can see here 2 by 2, here is a 2 by 2. Okay, this is the window for the pooling. And then apply the max pooling. Max pooling means we have to take the maximum value of this 2 by 2 grid. So maximum value here is, we can see here 3 minus 1 minus 3 and 1. It is maximum is 3. So output of the pooling operation it will be from this 2 is 3, the maximum value 3. And we have to shift this window again, right shifting, and considering a straight equal to. So a straight equal to, that means it will shift 2 bits. It means that the next pooling window will be this one. So again, we have to find out the maximum value. So here is maximum is 0. So here is the 0. And then we have to downshift. And again 2 by 2. So the 2 by 2 is, this is the 2 by 2 window. We have to find out the maximum value. So maximum is 3. So here is the maximum is 3. And again right shift using the straight 2. So here is 0, 1, minus 2 and minus 1. The maximum one is 1. So here is the 1. So this will be the output of our pooling operation if we apply pooling on the output of the convolution operation using the filter one. So similarly, if we apply the max pooling in the on the output of filter 2, so in this case again we can see, assume we have like 2 by 2 window for the pooling or pooling filter, and we have to select the 2 by 2 window. Here is the 2 by 2 window, and then find out the maximum value. We can see that here is the every values are just -1. So that means from here we will get -1. Then right shift. After right shifting the window, this is pulling window again 2 by 2, and we have to find out the maximum one. The max is 1. Max is 1. And then downshift after downshifting, we have to find out the 2 by 2 window and then find out the maximum value. Maximum is 0. And then find out those values, and maximum is here is 3. Okay, so that means this is the 3. So output of our pooling is this. Okay, so uh, we can see that actually original feature maps we have 4 by 4, that means total 14 values, total 16 values. But after applying the pooling operation, we can see that we have subsampled it and we have only 2 by 2, that means 4 values. So 16 to 4, that means huge reduction is there. So this is called max pooling. That means we have taken the maximum value of 2 by 2 grids. Sometimes we also use the mean pooling. Mean pooling, that means we will use the minimum value. Like on that case, if we here, in this case, we have to select the minimum one. So minimum is, you can see -3. Okay, so that means -3. And if we apply mean pooling here, in this case, we can see 3 minus 3 minus 1 0. That means we will get -2. Okay, so this will be the output of mean pooling. So another pooling types usually we also have, that is called the of those values. Okay, so if we apply the average pooling here, in this output, so average pooling will be like -1, here is a -1, -1, -1. That means -4 divided by 4, so it will be -1. Then -1, -1, -2, that means we can see here -3 total divided by 4, so it will be -3 by 4. And then this one -1, -1, -1, here is the -3, so it will also be the same value, -3 by 4. And in this case, -2 -4 is -6, and +3 and +1 is 4, so that means it is -2 by 4. So that means if we apply the average pooling, then output will be this. Okay, so these are the three basic pooling operations: max pooling, mean pooling, and average pooling. So most of the cases actually we use the max pooling, and sometimes we also use the average pooling. Mean pooling is not used many. Okay, so the pooling operation, why it is important and why it is necessary, because we want to reduce the number of pixels, or we can say number of samples. uh, so what it will actually benefited us, so it will benefited us, like if we have lower number of inputs, for the next convolution operation we need the lower number of so that's why pooling is necessary. But again, I need to mention that sometimes we usually avoid the pooling, because on that case, if there is a problem in reduction of your data, then we should not apply the pooling. So the CNN, now if we consider about the convolutional neural networks compression, then usually it will reduce the number of parameters to learn using these three principal methods. The first one is reducing the number of connections. It will reduce the number of connections. Then it will reduce the number of samples. So if we can reducing the number of parameters. Another way in this case is shared weights on edges. So same weights are shared with multiple connections. So here is also the same thing. That means we can see that the same weight, same filter value is here is connected both the first neuron and also in the second neuron. Similarly, so that means the weights are also shared. So same weights, or you can say same age value, is applied to different connections. In that way, also it will reduce the number of connections. Okay. Hello, am I audible?
Sir, you are not audible.
Hello. হ্যালো। আমাকে কি এখন শোনা যাচ্ছে?
Yes, sir.
ওকে। So did you actually understand the discussion on max pooling, mean pooling, and average pooling?
Yes, sir.
Okay. Okay. So if we apply the max pooling on this 6 by 6 image, at first we can see that we have to apply the convolution operation, and convolution on the output of convolution operation we have to apply the max pooling. Okay, pooling operation, and we can see that after pooling operation we will get this uh, new image, but we can say here the smaller image, or we can say a smaller feature maps. So here in this case we can see there is the image, the new image size or new feature map size is 2 by 2. So for each and every filter we will get like 2 by 2. image. Now we can see here that is the up at first in our first, this is our first convolution layer, and after that we apply the max pooling layer, max pooling, and we got these images. And then next what we have to do, this will be our input of convolution layer. But we can see that previously we have just one input, or we can say if we consider just one channel. But now we can see we have two inputs. We have two inputs here. Two inputs because we have two feature maps. We have applied two filters. So now we can consider we have two channels here. So that means this convolution operation, this convolution layer, it will get two filters here, or we can say output of two filters, two feature maps. And uh, each and every of this feature map pass through this convolution layer. And then again we will get the output of the convolution layer, and we will again apply the max pooling layer. Okay, so we can repeat this process several times. Now we have to think about that is output of output size of pooling layers, because to find out that is uh, to design our this convolution layer, actually we need to know the output size of this max pooling, output size of this max pooling. Okay, to design this next, or you can say second convolution layer, we need to know the output size of our uh, max pooling layer in previous step. Okay, so how to determine the output size? The output size is determined, we can see here, if we consider that we have W1, H1 and D1. Then for determining the output size, what we have to do, we need to know the filter size, and also we need to know the S is the straight filter size and straight. That means this filter size is about the pooling filter size. So it will that is, if we can say this is the input, then output will be, so W2, it will be width. The W1, that means the input size, this is our W1 width 1, minus of, here's the filter size F, filter size, divided by S, that is the straight, plus of 1. Similarly, for our H2, it will also be H1 minus F divided by S plus 1. And the channel number, that is D2, it will be the same as the D1. Okay. Uh, now consider that in our case we have applied, sorry, we have applied uh, we have applied here. You can see in this case it is the input size is 4 by 4, 4 by 4. It means that the W1 equal 4, and also H1 is all equal 4. There is width and height. This is also equal 4. So W1 and H1 both are equal 4. So if we consider W1 equal 4 and H1 equal 4, then now we want to find out the W2. So according to our equation, of finding out the size of our pooling operation, output size of the pooling operation, here is the W2 is W1 minus F divided by S plus 1. Okay? So now we want to find out the W2. It is W1 minus of F divided by S and then plus 1. So we can see that we have the input is 4 by 4. So here is the 4 minus of, uh, we consider our pooling filter size is 2 by 2. So here the F is 2, and then divide by, we have considered a straight equal 2. So here a straight is 2 plus of 1. So in this case we can see 4 minus 2 is 2 by 2 plus of 1. So it is 1 plus 1 actually 2. So that means width of the output of pooling size, it will be 2. Similarly, we can also calculate the H2, okay, H2, and you will get the H2 equal to also. So that means this is the equation. Using this equation, we can find out the output after the pooling operation based on the filter size, that is a pooling, and a straight, and also the input. Okay. Okay. Now we can see here that is we have applied the convolution, then pooling, and then again convolution, and then pooling. In this way, we can apply the several iterations. But after that, what we have to do, the next thing is flattening. That means we have to do the flattening. So what does flattening means? So in this case, we can see that means after the max pooling, we will get the feature maps again here. Then those feature maps values we have to pass through a fully connected feed-forward network. So for the feed-forward network, we can see that that is the input. It should be just one dimensional. So that means there is no way to just put the input in 2 dimension, 3 dimensions. So that means we need to do the flattening on that case. That means we have to convert all those data in one dimension as one dimensional values. So that's called the flattening. That's called the flattening. Okay. So here, that means we need the flattening operation to make the data to a one-dimensional form. That means we need to prepare the data for our fully connected feed-forward network. That's why we need to do the flattening. Then how to do that? So now we can see that that means we got there is 2 feature maps. Maybe you can say those are the values of the feature map. Then for each and every feature map, what we have to do, we have to just convert it to one dimension. So uh, that means this data we can represent like this way. That is 3, 0, 1, and 3. And then we can say here is the 1, so minus 1, 1, and 0, and 3. Okay. So here is the minus 1, 1, 0, and 3. So it means that there is the 2 by 2 of forms of data. We have to represent there is 2 by 2 forms of data. we have to represent using like one dimensional. So it will be this 1 times 2 by 2 is 4, this dimension. Okay, so this dimension. So that's why it is mentioned here like 3 0 1 and 3 minus 1 1 0 and 3 in this way. And now we can say these are our one dimensional data. We can easily feed this data to our fully connected feed-forward networks. So in this case, we can see if we now want to design the fully connected feed-forward networks, then how many neurons we have to use in our input layer. So in this case, we can see that is it will depend on our, that is total number of total number of feature maps, and also it will depend the size of the feature maps. Like in this case, we can see we have two feature maps. So two feature maps we have, and the size of the feature maps are 2 by 2. So that means how many neurons we need at the input layer of the fully connected convolutional neural network. So fully connected feed-forward network, on that case, we can see it is total 8. Okay, so that means in this layer we have to add 8 neurons. 1 2 3 4 5 6 7 8 neurons. So we know that from the discussion of our neural networks, that means we need to design the input number of input layer neurons. So here we can see we got the number of input layer neurons, it's 8. And we have to design also the number of output layer neurons. So it will depend on that is the number of class we have. Like if we consider the 4 class, then we can have the 4 neurons in this case. Okay, so that means the fully connected feed forward network, this one we have to design based on the principle of our neural networks. So whatever we learned in our neural network, this is a kind of the neural networks also. Okay, so the input and output is done. Then there is number of hidden layers. It is user defined. It is user defined. User can consider maybe 3 layers. User can consider 5 layers. User can consider 10 layers, or user can consider 1 layer also. And how many neurons will be added in each and every hidden layer, that will also be depend on the user input. That means user can define that network also. And another thing is here in case of this, that is we can see it is fully connected. Okay, fully connected, but we also apply some form of actually dropout. That means no need of all those connections. We can drop some of the connections. Okay, some of the connections with a percentage, like 20% of the uh, connections we can drop. So that's what another approach. That means for reducing the number of connections, reducing time to upgrade the weights, uh, reducing also overfitting. It's better if we drop some of the connections. That is called the dropout. So dropout percentage, like maybe the connections we can drop maybe 20% or 10%, okay, of the connections. But in this structure, we can see that it is a fully connected feed forward network. That means each of the neurons of one layer, it will connect to the network, the next layer. Okay, every connections will be we should establish kind of a mesh connections. Hello. So do you have any question up to whatever we discussed regarding the flattening and fully connected convolutional neural networks and the pooling operations?
No, sir.
Okay. The next, we have to now consider how to count the number of learning parameters we need to update. This is very necessary, specifically need to count the number of parameters, because if you design a network, a customized network, and if someone also design another network, then we need to compare between the learning parameters of yours and also learning parameters of other networks. Because that means if we apply huge learning parameters, that means we need to update maybe many learning parameters. This is a negative side of your network. That is the simplistic design, and also reducing the number of learning parameters is also one of the goal of designing CNN. For efficient design, you need to consider the learning parameters, that means number of learning parameters you want to update in learning time. And also you need to consider about your efficiency, or you can say the accuracy of your model. So both are important. So that's why we need to calculate, that is how many learning parameters you have in this network. So consider that we have input. So we have input, and the input size in this case we can see that is the input size. Input size is here is 28 by 28. Okay, so that means, so consider one input size here. This is, consider just image. We can see it is 28 pixels width and 28 pixels of height. And we can consider this one is just only black and white uh, pixel, black and white image. Or we can say here, in this case, we can say channel is 1. Okay, channel is 1. Channel is 1, it means that it is a kind of black and white uh, image. So if this is the input, okay, if this is the input to this convolutional layer, to this convolution layer. In this convolution layer, then we have to think about there is the properties of the convolution layer. Usually we can, if we consider that this convolution layer, in this case we can see here is 25 3 by 3. That means the filter size is 3 by 3, and we have 25 such filters. It means that here is, in this case, it is 25 3 by 3 filters. The filter size is 3 by 3. And how many filters we have? Total 25 filters we have used in this case. Then we need to think about that is okay. If we apply this much filters, then how many parameters we have to learn? Okay, how many parameters we have to learn? And then next here, after that, we applied here the max pooling operation. And it is also mentioned that is for the pooling, we have to think about our that is the size of the pooling filters. In this case, if we define the size of the pooling filters is 2 by 2, that means we applied here 2 by 2 filters. Then what will be the output of the pooling? Because based on the output, the next convolution operation will work. Okay. Uh, So that means this is how we have to consider our that is uh, we have to calculate our number of parameters. Now, so in our example we can see there is the input size is 12828. That means 28 by 28 and just only one channel. That means the kind of black and white. And then the convolution of we applied this 25 3 by 3 25 3 by 3 kernels or filters. Then what will be the output of that, and also how many parameters we have to learn on that case. So in this case we can see so if we consider our uh, convolution operation at this case uh, then then what will be our feature map size of the feature maps. So we have 28 and uh, minus of the filter size is what, 3. Then here is the 28 minus of filter size is 3, and then divide by our straight is straight considering the straight is 1, straight equal 1, and uh, plus of 1. So it means the feature map size after first convolution it will be 28 minus 3, that is 25 plus 1, that is 26. So 26. We have already know how to calculate the output size of convolution operation from this discussion. We have already discussed that. So here is this. So for convolution and neural networks, so we can see in this case that is for the valid we have this m minus k plus 1. If we consider about our straight, then considering a straight, then the output size will be this. So actually we are using this equation for calculating the output size. So m minus k plus of s divided by s. Okay, so m minus k plus s divided by s. So we are using this equation. Okay, so using that equation we got what? We got this, that is is it right? So here is this, that is m minus of k plus s divided by s. Okay, okay, the same thing. I think you can write it a little bit different way. So in this case m is what? M is our input size. So here is the m, this is m, and k is our filter size. It is 3, and s we consider the s is 1. So straight, if we consider straight is 1, then we can see here it is m is 28 minus of k is 3 and plus straight is 1 and divided by the straight is 1. Okay, so that means it is 28 minus 3 25 plus 1 26. Okay, so here is the 26. That means output will be so output will be 26 times 26. This will be the output of feature maps. But how many feature maps we will have? For each and every filter, we will have just one feature map. Then how many filters we have applied? So here is we can see 25 feature maps we have applied. So it means that uh, we will get 25 feature maps. So this will be the output of the convolution, first convolution operation. So now we have to think about like that is how many parameters uh, for each filter. How many parameters for each filter? So we can see the filter we have 3 by 3. Okay, so that means the kernel we have 3 by 3 kernel is used. So 3 by 3 kernel size is 3 by 3 in our case. Kernel size is 3 by 3. The 3 by 3 kernel, that means how many parameters are there? Total 3 by 3 equal 9. Total 9 parameters. Okay, so for each kernel. But how many kernels we have? So in this case, we can see there is the number of kernels we have. The number of kernels we have 25 kernels. Okay, 25 kernels we have. So each and every kernel has 9. That is learning parameters or nine words. Then if we have 25, then 25 times 9 parameters we have to learn. We have to learn for this. That is convolution layer. Then after that we have to apply the max pooling. If we apply the max pooling, then what will be our output size? So in that case, the output size will be, that means we can see that is for max pooling. The output size usually we calculate using this equation. That is W minus F divided by S plus 1. So usually we consider the S in this case, that is the straight equal to, that is the default. Uh, so W minus F plus divided by S plus 1, if we apply that, so here, that means we can say this is our input size. So W is 26 in this case. This is our W, or you can say W1. And we consider the 2 by 2. So 2 by 2, his F is F, F, F is 2. And we consider the default value of our stray, that is 2. So then the W2 will be, it will be W1, that means 26 minus of F, F is here 2, divided by the straight we consider the default is 2, and then plus of 1. It means that 26 minus 2 is 24. 24 by 2 is 12. 12 plus 1 equal 13. So here is the 13. Okay, so here is the 13 and here is also the 13. That means the after max pooling we will get the feature map size 13 by 13. So this will be the feature map size. But how many feature maps we will get? We will get the 25 feature maps. Okay? 25 feature maps. So here is 25 feature maps. So we will get 25 features. Now that means for the next convolution operation, this will be our input. It means that we have 13 by 13, you can say 13 by 13 image. And how many channels we have? We have 25 channels now. Previously here, as the input size, we can say we have considered just one channel for the first convolution, this convolution layer. But for this convolution layer, how many feature maps we have? We have 25 feature maps. That means the channels here is 25 channels. Okay, now if we consider that in this convolution layer, it is we applied also again 3 by 3 kernels, 3 by 3 kernels, and this time we applied 50 filters, 50 filters. Then at first we need to find out that is our output of the convolution. Okay, we can see that is input is 13 by 13, input is 13 by 13. So on that case it will be, that is here is m is 13, so m minus that, then then k, in this case what, k is our filter size is 3, then plus of straight, consider the straight is 1, divided by 1. So in this case we can see 13 minus 3 is 10 plus 1, so the output will be 11. Okay, so that means we can say we will get 11 by 11 feature maps. How many feature maps we will get? For the 50, we will get 50 feature maps. We will get 50 feature maps. So this will be our that is the the convolution. But we can see here actually we have 25 inputs. For each and every input we will get 50 11 by 11. Okay, 50 11 by 11. So for 25 we will get 25 times 50 times 11 by 11 total this much uh, feature maps. Okay, so now if we want to count the how many parameters for each filter, how many parameters we will get. So we can see that here for each filter, here 3 by 3, that means for each filter it is 9, it is 9, but we have 25 channels, 25 channels, that means we have 25 inputs, and all these 5 inputs we have to pass through this uh, 3 by 3. So that means that the for each filter we will have 25 times 9 parameters. So that means here the channel number is 25, and that's why uh, for each and every channel we need to have different filters. Okay, so that's why 25 times 9 total number of that is for each filter we will have this many parameters. Okay, now what we have to do, we have to do the max pooling, and for the max pooling it is like apply the 2 by 2, apply the 2 by 2. Then if we apply the 2 by 2 here, uh, that means our input size is 11. So in this case we can say the w is 11, w1 is 11, so our w1 is 11 minus of then minus of w1 minus of f, and in this case f is 2, then divide by the straight, and divide by the straight, and then uh, here is our plus 1. Then we will get a fractional value. In this case we can see 11 minus 2, that is 9. 9 by 2, it is 4.5. 4.5 and plus 1, it is 5.5. 5.5. Okay, so 5.5. So this is a fractional value. So in this case, what we have to do, there is there is, after this operation, pooling operation, we will not get actually the 5.5. So we will get what? We will get the floor of this. We have to do the flooring. So that means it will be the 5. So here the 5 times 5, you can see that is our output of max pooling, output of the max pooling. And how many feature maps we will get here? For the 50, we will get here the 50 feature maps for max pooling operations. So then we can see here there is 55 by 5. Then what we have to do? We have to do the flattening. So if we do the flattening, that means it will convert to one-dimensional video. That means we can say 50 times 5 times 5. It is 1250. That is 1250. This is one-dimensional data. That means 1 times 1250. So then what we have to do? We have to just feed this one to our fully connected feed-forward networks. So that means in this input layer, we have to have 1 to 50, 1 to 50 neurons, 1 to 50 neurons. And then based on your design, so it will be depend on you. So in this case, we have designed like the 100 and then 10. Okay, 100 then 10. That means in this layer, we have to have 1 to 50 neurons, and next layer we have added 100 neurons. That means uh, after this one we have just added one layer. So in this layer we have 100 neuron, and then the output dimension 10. Okay, so here is the you can see there, this is the output dimension. Last one, we have the 10 neurons in this case. That is, we have 10 classes, and apply the softmax there. So softmax, we will get the probabilistic output on that case, okay, using the softmax. So this is how we need to design, and this is how we need to calculate our number of parameters, okay, number of parameters. So in this case, we can see that is, it is mentioned that, so it is mentioned that how many parameters for each filter. So each filter we can see in this case 9. But if it is mentioned that how many parameters for total, then what we have to do? For each filter it is 9, then total 25 filters. So that means we can say that how many parameters total, it is 9 times 25, because we have 25 filters. Okay, so that means how many parameters for each filter, it is mentioned how many parameters each. But if it is mentioned how many parameters in total for this layer, we can say the total number of parameters, it will be 9 times 25. And for the max pooling, actually there is no updates of the weights. In max pooling layer, there is no parameters to learn. But in this case, there is the convolution layer. Again, convolution layer. We can see here there is we need the parameters to update. So here it is mentioned that how many parameters for each filter. So we can see that that is we have 25 times 9. So for each filter, this much parameters we have to update for each filter. But how many parameters in total? We can see we have 50 such filters. Okay, 50 such filters. That means for total we need to consider 50 times 225. The total number of filters or total number of weights we need to update, like 20 times 250 225. So in this layer, total number of parameters we need to update is 50 times 225. In this layer, 9 times 25. Okay, then again we can say max pooling. So in max pooling layer, there is no there is learning parameters to update. Okay, so now what we have to do, we have to think about the next. After max pooling, we do the flattening. Okay, so we do the flattening, and it will we have like 1250. In this layer, we have 1250 neurons, and then next layer we have 100 neurons, and output layer we have 10 neurons. So if this is the design, then we have to consider about, that is how many parameters we have to learn in our fully connected feed-forward networks. How many parameters we have to learn? So in this case, you can see that is 1250. So 1250 neurons we have in our input layer, that we have to, each and every one is connected to like 100. So here is a 100. So everyone is connected to each and every of the neurons of the next layer. So that's why how many connections in total? 1250 times 100. Okay, 100. And now what we have to do, we have to consider again the bias also. So how many bias we need to add it there. So in this case, you can see there is 100 neurons in our hidden layer. So we have to add each neuron just one bias to each neuron. So that means you can say we have to add 100 in that case. Okay. So this is for the number of parameters from input to hidden layers. Then plus of we have to consider now that is hidden to output layer. So now we can see in our output layer we have 10 neurons. We have 10 neurons. So here is the 10 neurons. And then uh, actually each and every neuron is also connected to there is the previous layer. So previous layer we have 100. So you can see here it will be 100 times 10. So this many connections we have in hidden to output neurons. And each and every connection just we have to have one weight. And plus of in our output neuron we have 10 in our output layer we have 10 neurons, and each and every neuron we have to add just one bias. So that means 10. So this many weights we need to update in our hidden to output layer. Okay, so then total number of parameters, if we want to count the total number of parameters in this network, then we have to think about this one, that one, and then previously we have, that is 50 times 225 plus of 9 times 25. That will be the total number of parameters we need to update in this uh, convolutional neural networks. So any question from your side?
No, sir.
Okay, then thank you very much for attending this session, and see you in our next lecture.
স্যার 427 এর ফাইনাল সিলেবাসটা কবে দিবেন?
আমার মনে হয় যে আমাদের তো শেষ ক্লাস হচ্ছে এর
স্যার
পরের ক্লাসটা
থার্সডে
সম্ভবত।
হ্যাঁ হ্যাঁ।
হ্যাঁ, এর পরের ক্লাসটা। ওখানে আমরা সিলেবাস নিয়ে ডিসকাস করবো। হ্যাঁ,
আচ্ছা স্যার। স্যার আপনার সাথে একটু কথা ছিল যে আমি মিডের আগে এই আপনি